Hi there, this is Prof. Johan from the Department of Chemical Engineering at the University of Pretoria. Welcome to my series on the Introduction to Chemical Engineering and Chemical Engineering Principles.
Good morning, guys. Let's quickly spend another 5 or 10 minutes talking about the example we did in class yesterday. So we had the system as indicated in the diagram, where we have some streams going into a process and then leaving the process in stream C, going into another process and leaving in stream F. You can remember that we took this and then converted it to a nodal approach so that I could teach you how to do this in one go without thinking. And then we ran into a problem where I couldn't get all the equations sorted. So I'm going to quickly show you what are all the equations so that you can sort this mass balance without thinking about it. Here you go. You can see that we've taken this mass balance and changed the two unit ops into two nodes. Nothing else has changed. Next, by analyzing the system, we now see that we have two nodes around which we have a change in mass. And that's where we can do mass balances. We also have 6 streams in total in the system. 1, 2, 3, 4, 5, 6. For which we need to understand that we have a composition and a flow rate. There's 5 components in the system, and strictly speaking it means that there will be 5 components in every single stream. So there, for instance, 2 of the components are missing. Next, we can use this knowledge that we have 2 nodes, 6 streams, and 5 components to do an analysis on the system. We need to figure out how many variables we have first. And the variables are going to be in every stream, let's say for instance stream E, the 5 fractions for the 5 components plus that stream's flow rate, giving me 6 variables per streams, and because there's 6 streams, we're going to end up with a total of 36 variables. So let's do the analysis. Variables 36, and we got that by saying there's 6 streams with 5 components and 1 flow rate, giving me 36. Next, we need to go calculate the knowns. You can also refer to this as assigning equations or knowns. And we get to this by counting everything that is given to us that we know. 1, 2, 3, 4 compositions in stream A, 5, 6 with the compositions in B, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and including this flow rate, 18 knowns. So we can add this on here. And that is it. We now have a total of 36 variables, 18 knowns, and if we subtract these two from each other, we know that we have 18 unknowns. If we want to solve this problem, we need to now get 18 equations for us to solve this. If we have less than 18 equations, the system is underspecified, and if we have more than 18 equations, the system is overspecified. Let's look at what these equations will be. The first equations we're going to use is the easy one. It's the sum of the fractions will be equal to 1. Now, how many of these are there? There's going to be 1, 2, 3, 4, 5, 6 of these. So we have 6 sum of fraction equations to add. The next set of equations we can use are the component balances. So how many component balances do we have? Remember, we discussed this. Everywhere where you have a change in mass, you can do a balance, a mass balance. In this case, we have 5 components, so we can do 5 component balances here and 5 component balances there. So we end up with 10 component balances that we get by doing 5 component balances over 2 nodes. Now looking at this, you can see that we have added 16 equations. So we are still short. We can't solve this problem. And I told you yesterday in class that when I did this the night before, I got this piston to be overspecified. So there must be some other equations here that we can use to solve this mass balance. And guys, this is where things get a little bit difficult in a problem like this, and where, although this is a recipe, you still have to apply your mind a bit. When you look at the system, let's just spend 5 seconds talking about this. If I look at this composition, I have 1, 2, 3, 4 of the 5 components. If I add these up, they add up to 100. And by adding them up and getting to 100, I know that the fraction of the inert material here should be 0. And perfect. I have used one of the sum of the fractions equal to 1 equations to get to that. Okay? Now, I want to go generic, so I don't want to write this 0 down for the inert under the assigning variables or assigning equation, the known variables or assigning equations. I want to write down all the equations I have to solve it. So there is one equation here that I use to solve what's going on in stream A. Now the trick comes in, and this is what I missed in telling you yesterday. And unfortunately, we humans are so into recognizing patterns and seeing things that sometimes converting them to equations is difficult. Look at stream D. When we add this up, we also get 100. And now we know that there is no sodium chloride and no inert materials in this line. But I cannot use one sum of the fraction equations to solve for two knowns. So if I say all this adds up to 100, and for that reason those two are 0, I have used one equation to solve for two unknowns. And you know you cannot do that. You can't solve two unknowns in one equation. I need 2 equations to solve it. This implies that there is another equation except for the sum of fractions that I need to use to solve for those two unknowns here. And this is what I missed yesterday. Like I said, I figured it out the evening before, but yesterday I was just too dumb to remember again. So let's look at this. What is the extra equation that we have in here that's going to help us to use one sum of fraction equations but get both those two zeros? And it's actually easy. Think about it. When I say 2 plus 2 plus 96 plus some value equals to 100. That already adds up to 100. Then I know that the sum of those must be equal to 0. And this is the other equation that we missed. By understanding intuitively, we know that if this is a sum of fractions, that must be 0 and that must be 0. But there's still a mathematical way to write it down. And the mathematical way to write it down is to say that there is an equation where X, sodium chloride, in D, plus X, inert, in D, must be equal to 0. And that's the additional equation, 1. But there's one other thing we need to do. We need to say that all x's must be larger or equal to 0. Otherwise, this can be 10, this can be minus 10, and I still get a 0. But I can't have a negative fraction. We know that. So the complete equation is this. The sum of the fractions of the things that is not listed in my table, so those 3, must be equal to 0 because the sum of fractions in there equals to 1, and it's already equal to 1. Everybody follow that? I'm hoping you follow that. So it means that the one additional equation I have is in stream D. Because I have 3 components, the other 2 components must add up to 0 for this to work. And obviously, I'm going to have exactly the same thing in stream E. And there we have 2 additional equations. But what about what's happening in stream B? It's not changed. It is exactly the same equation, except for the fact that there's now 3 fractions that we need to take into account. But everything is still the same. And there you have it. Now we have all the equations. These we tend to forget about because intuitively, if the sum of 2 components in a 5-component system adds up to 100, which that does, then the rest must be 0. But there's still a mathematical way that we can write that, and that is this. So it's important to know that although I know this, I should still be able to write down the math. And now, if we do our degree of freedom analysis, we're going to say, I have 36 variables, I have 18 assigning equations or knowns, and now I can add them all together, 19, and this 19 is made up of 6 sum of fractions, plus 10 independent component balances, plus 3, all the remaining components in the stream must be equal to 0 equations. Adding them up gives me 19. If I now subtract, I get -1, and the system is over specified. Okay, guys, so regarding yesterday's lesson, I'm not as dumb as I look sometimes. So you can solve this with a recipe base. It's just important to know which equations to use. And being as dumb as I look, I missed these 3 yesterday. Alright guys, I hope this helps you. I'm going to post this on ClickUp now, and I'll also post this video on the CRR WhatsApp group so that you can have a look at it. Have a good day and good luck for tomorrow's test.